So there's also something called a flux line integral. We'll talk about that for a moment. It's an alternate type of vector line integral. So previously we talked about the fact that we were extracting the component of the vector field that was tangent to the curve. But there's another possibility. What if we extracted the component of the vector field that was perpendicular to our two-dimensional curve? How would we calculate that? Why might it be useful? Okay. Well, how do we get the perpendicular component? So of the vector field, you want to take the dot product with the unit normal. So this might be useful if we want to find something happening across the curve. So the way I like to think about this is, imagine that fluid is flowing across our curve, like water crossing a net. So the integral over the curve of f dot unit normal n ds is called a flux line integral. We also say it calculates the flux of f across c. So how does this work? So to calculate a flux line integral, as with every line integral, we need to make a parametrization. So again, recall that our curve r equals xy. It's got a tangent vector, which is r prime equals x prime y prime. We know once we have a tangent vector in two dimensions, we know how to make a normal vector. The normal vector is you just switch in two dimensions, you switch the components, make the second one negative. So we know that we have a normal vector, which we're going to call little n, and that's y prime comma negative x prime. But we want, for a moment, we want a unit normal. So we're going to have to divide by the magnitude. So notice that the magnitude of r prime is the same as the magnitude of n. Since they have the same components, the components have the same magnitudes, therefore the vectors have the same magnitudes. So of course the unit normal just comes from taking the normal vector we have here and just dividing by its magnitude. And then let's also recall that ds is just the magnitude of r prime times dt. So put that all together, and what do we get? We know that the flux line integral, the integral over the curve of f dot unit normal n times ds, let's just rewrite that. We know that unit normal is just this normal divided by its magnitude times ds was just magnitude of r prime dt. But look, we're dividing by the magnitude of the normal and then multiplying by the magnitude of r prime. We just said those are the same thing, therefore they cancel. Those magnitudes are the same, therefore they cancel. This will just give us the integral from T1 to T2 of vector field dot the normal vector, which we know how to make, dt. So we could also, so this is written in parametric form. What if we want to write this out in coordinate form? Well, let's take a look. Since, as we just said, the normal vector, not the unit normal, the normal vector is y prime comma negative x prime, then normal vector dt would just be y prime dt comma negative x prime dt. But what is y prime times dt? That's just dy. And what is negative x prime dt? That's just negative dx. So therefore, f dot n dt is just f dot that vector, which just gives you pq dot that, so p dy minus q dx. So I usually like to write the dx component first, but you can write them in either order. Sorry, not the terms first. So therefore, the flux line integral can also be written as the integral over the curve of negative q dx plus p dy. And in fact, that will often help us do the calculation. In fact, let's take a look at how we do a calculation. So for this vector field, f equals x plus y, comma, x minus 2y, and then this curve, r equals t squared t cubed, t goes from 0 to 1, calculate the flux of f across C. So what do we need to do? We need to make our parameterizations. So first, this is given parametrically, so we're going to have to write this out parametrically. So what is n? N is y prime, our normal vector n is y prime comma negative x prime. So that is 3t squared comma negative 2t. So next we need to write down the parameterization for vector field f. So that's pretty obvious. X plus y will just be t squared plus t cubed, etc. So the flux is the integral over the curve of f dot unit normal ds, which we know we can just rewrite as the integral over f dot normal n dt. So that equals, when we know the boundary t values, 0 to 1, f written parametrically, t squared plus t cubed, comma, t squared minus 2t cubed, and n we just figured out was 3t squared comma negative 2t, and then all of that dt. Next. Now we just calculate. Take the dot product, simplify algebraically, and you get the integral from 0 to 1, 7t to the 4th plus 3t to the 5th minus 2t cubed dt. Now the integral is set up. It's a very easy integral to actually do. Do the integral, evaluate from 0 to 1, and you just get 1.4. Okay. So now that we've talked about all these different types of line integrals, I'm going to skip that problem for time. I just want to sum everything up. So here's everything all together. All these different types of line integrals. Scalar line integral. The basic formula is the integral over the curve of scalar function f ds. And notice that if f represents a height, this is an area. If f is a probability density, it represents probability. If f is a mass density, it represents mass. Okay. Next, vector line integral was the integral over the curve of vector field f dot dr. And if f is a force, it represents work. Okay. Next, we also saw a scalar line integral in coordinate form, the integral over the curve of p dx plus q dy. We also saw a vector line integral with respect to s. So that was the integral of vector field f dot unit normal t ds. And then we also just saw the integral over the curve of vector field f dot unit normal n ds. And that's a flux line integral. And in this case, if f is a velocity field, that gives you the flux across C measured in volume per time. And then written in coordinate form, the flux integral is the integral over the curve of negative q dx plus p dy. And then just a couple things about the parameterizations are right there.